understood doing things like that. So we kind of brainstorm and stuff.
That's okay. So, all right, I will begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. I thank you again for this class, and for this time we have to meet together. Help us to understand the math, please, Lord. In your name I pray. Amen. All right, so let's see here. This is theorem, and my apologies in advance for the camera. This is the new version of this camera, which there may be a way to turn the autofocus off, but I can't figure it out. And unfortunately, it'll get fuzzified sometimes, and sorry about that. Hopefully, we'll be able to see everything. Be a closed proper subspace. Let X be a closed proper subspace of a norm space E. NLSE for every epsilon greater than 0, not greater than 0, excuse me, for every epsilon element of 0, 1, my bad, there exists X sub epsilon in E with the length of X sub epsilon equal to 1 and the norm of X sub epsilon minus X greater than or equal to epsilon for all X in X. So this is known as Ries's lemma. All right. So what's this saying? Before we try to prove it, just for a second, let's just try to put it into words. What is this? What is this saying? If I draw a picture, if I foolishly try to draw a picture, right? Like here's the, what was it called? Well, if this is X, right? Well, that's not what I want to draw. So X sub epsilon's like in here, right?
Yeah, okay.
Maybe it's on the, this is the one
Right.
closed, the sphere, right? And the unit sphere, centered at the origin, I suppose. And then, so for any X, let's see here.
Oh, right. Yeah.
There exists
epsilon inside the sphere.
So let's see here. There is a, for all X, sorry, I'm just having trouble, how can that be true? What about X equal to X sub epsilon? Oh, X is a closed proper subspace. So X, okay, I've got the wrong mental picture. X is not E. X is the closed proper subspace of E, right? So maybe, I mean, a picture of x.
Okay, so theoretically, the x of epsilon could not be in x.
Right.
Since, yeah, okay.
But it seems to me like it could be, though. But I guess, well, okay, but there exists x of epsilon. So you don't, obviously you do not pick x of epsilon in x, because that would be dumb. Don't be dumb like me, right? So this is x. X is a proper subspace. It goes to the origin, right? Zero's here. And so for any x, for any point x on the proper subspace, what's the situation? Right? This distance, this right here, this vector, right? This displacement vector, which would be x minus x of epsilon, right? Or excuse me, epsilon, words. X of epsilon minus x, right? That vector, that has to be greater than or equal to epsilon. Now I start to understand why the epsilon has to go from 0 to 1. See, because, you know, well, I mean, like the farthest, that's distance 1 from the origin, where x, I don't know, I thought I saw it, but maybe I can't explain it. Okay. All right, let's look at the proof then. All right, so he says, let z be an element of E take away x, right? So in the complement of x in E. And he says let D equal to the infimum of x in x norm of z minus x. He says since x is closed, d is greater than 0. Let's see here. So x is...
Z's not in,
What's that?
because he's not in the set, x is in the complement.
Yeah, z is in, so x is closed, which means e minus, so this is open, right?
Yeah.
And if that's an open set, I mean, I can try to draw a picture again if you want, but I mean, if this is my x, right, and z is here, then, and there's an open set around that, right? Then, since, I mean, z is not on x, so there has to be, well, I suppose if d was equal to 0, then that would imply, wouldn't that say that, yeah, wouldn't that say z is an element of x? I mean,
Yeah.
I think, since x is closed, it would imply, anyway, okay, so then, let's see here, where was I? He says if epsilon's an element of 0, 1, then what? Then d is less than or equal to z minus z. Wait, what's z naught? Oh, my bad, x naught. Wait, what's x naught? I think I missed something here. Oh, okay. Then d is less than or equal to the norm of z minus x naught is less than or equal to d over epsilon. So, okay, so we said that the infimum is positive, right? And of course the inf is less than or equal to this, and this is then for some, this is for some x naught, where for some x naught in x. Where's z taken from here? All right, z is the, thank you, z is that fixed point to start with. Okay, cool, same z. All right. So this is clear because d is the inf, right? Yeah. Which isn't to say that when you plug in that this is equal to d, right? Okay. And then let's see here. What's d over epsilon? Well, since epsilon's epsilon's from 0 to 1, that makes 1 over epsilon a number larger than, I'm not quite clear why the upper bound is there.
Well, this may not be the right reason, but if d is the infimum, then epsilon times the norm z minus x naught, so less than equal to d, would make sense in the sense that since epsilon is in the open set 0, 1, then any epsilon that interval would make that whole quantity smaller or the same as d. I don't know. It's not very rigorous.
I'm not saying you're wrong because I'm not. I'm drawing a blank here. There's got to be something obvious, of course, but I mean, obviously 1 over epsilon is a number larger than 1 here, right? Yeah. But the claim is that that's true for any okay, so x naught's not just any.
It's specific. You can pick one specific.
Like yeah, I think that's a reasonable claim. Like, excuse me. So for a given epsilon, right? You can pick your x sub naught like here, right? Suppose this is x sub naught, I mean, first of all, suppose epsilon is a half, right? If epsilon's a half, then, excuse me, you can pick an x naught which is what? Like this can't be what? No more than 2, right? So as long as you pick an x naught which is like, within 2 units of z, then you've got the upper bound. And since this is the inf, I suppose if we get, okay, anyway, I think it's reasonable. I'm not sure quite how to, I'm not sure I know how to prove it directly, but it does seem like a reasonable claim. Okay, so then once you have that, then I think it's easy to go from there, because then you let x sub epsilon equal to z minus x naught. Z minus x naught over norm of z minus x naught. Right. Now z minus x naught is non-zero, so that is, you know, the normalization. We're taking vector dividing by its length. So this, of course, has the length of the candidate x epsilon equal to 1. And then what else do we need to do? We need to show that, you know, pick any x. For any x in x, we need to look at the norm of, where was I? X minus x sub epsilon, excuse me, x sub epsilon minus x, right? And we'd like to show that that is greater than or equal to epsilon. And so let's see here if we can do it. Here, I'm going to give you back your book for a minute.
Sorry.
I've been depriving you of your book too long. All right, so we know what x epsilon is by our construction. It's z minus x naught divided by the length of z minus x naught. Minus x. All right, then what? Does he do the greater than triangle inequality thing next?
Before that, he takes out the norm, since it's in the reals, he just distributes it out.
Oh, he factors the norm out.
Then he does.
So like this. So if you got to use your imagination a little bit, but there's a x times the norm of. All right, I'll buy that. And then he uses the triangle inequality maybe. Greater than or equal to.
The one, the inverse of the norm times d. That's what he says next. Since the inequality laws, since it's a subspace. Sorry, yeah, sorry.
It's
book two.
It's okay.
Since it's a subspace, this quantity is in x as well, and so these the infimum of quantities in x, and that's in x. We can.
Oh, so he's just. Okay. So then, actually, no, it wasn't the triangle inequality. It's something.
The subspace hypothesis.
So you said z minus. Where is z from? Z. No, where is z is from the complement, right?
Yes, z is complement.
So z is. Let me just collect my things here. Z is an element of e minus x, right? Where's x naught?
X naught's in x.
In x.
Okay. So z at the beginning stays there, and so the quantity that is z minus the quantity x naught plus x times that norm is in x. Because
Minus x times the norm?
The inside the norm, z, yeah, that the whole quantity is z minus quantity. I'm distributing the negative out. Z minus the quantity x naught plus x times that norm is in x, because x is a subspace. Okay.
So, wait. Z minus the quantity x naught. Oh man,
Yeah.
I'm sorry. Ooh, what have I done? I don't know why I gave you back the book. I'm an idiot. Oh, it's okay. I know where we are. Z minus x naught minus, yeah, okay. Using the fact that x is a vector subspace, huh?
Because X dot's in X, and X is in X, and then the normals are the.
Oh. So you're talking, so this is like, this can be rewritten as like Z minus, let's say X1, where X1 is an element of X again, because.
And say X1 equals all that.
Yeah, okay, that makes sense, because this is an element of the proper subspace, and this is a scalar multiple of an element of the subspace. So by subspace test, that's an element of the subspace.
Yeah.
But then this is Z minus X.
But that, yeah, the whole point equals that, but we said D was the infimum.
Right.
Of the set.
So this is, at the moment, this is just equals.
Yeah, and all of that is superior to
The D
that inverse norm, or D over that norm.
over Z minus Z naught, yeah.
Yeah.
And then what?
And then you have
Why do I have a Z naught? That's an X naught. I'm an idiot. I'm just
Oh, sorry.
corrupt. These formulas are getting corrupted by my who's the weakest link. I am. Let's see here. So yeah, that was what?
But then we just have Z from the inequality replicating there. We actually say that's greater than to yeah.
Epsilon. So that's just coming from this here over here.
Right. Yeah.
Yeah. All right. Sorry, I have taken entirely too much time for this lemma, but I guess it's an important one because it's what allows us, like, it's the, linchpin here to the next theorem, which is that a norm space E is finite dimensional if and only if the closed unit ball in E is compact. All right, so let's try to go through the proof of that. Hopefully this one will go better. I just want to be the Banach spaces.
I'm sorry.
Oh, well, yeah, it's fine. Ooh, I should have probably taken a picture of that, but.
Oh, I had a picture of the picture you drew.
Oh, well, that's good.
Not that.
Let's see here. All right, so I don't know. I don't think I added anything of terribly profound value to the book or anything here anyway. But so yeah, a norm space E, normed linear space E, is finite dimensional if and only if a closed unit ball in E is compact. All right, so here's his proof. Let's look at it, see if we can understand it. So he's like, if the dimension of E is equal to n, let E1, E2, En be basis, right? I mean, that's the definition of finite dimensional. By theorem 3.1.13, we can assume without loss of generality that the norm, so then, remember by the equivalence of norms, we can without loss of generality, we can use the norm to be, the one where we just do what? We pick off the absolute value of the coordinates with respect to this basis, yeah? So we called this like the zero norm or whatever in the proof. All right, great. And he says, it's a simple exercise to show that the unit ball with respect to this norm is compact. So what does it take to show? To show it's compact, is that the only thing we have? Do we have any other equivalent characterizations of compactness, or not? That's kind of it? I'm not asking in such a way to tell you that there is something. I'm actually asking.
Oh, no, I'm sorry. Yeah, okay.
I don't. Yeah, I've got your book.
Okay.
um,
Sorry. I didn't catch it.
I think that might be it at the moment. To remember. I mean, we had the theorem that compact. How did it go? Oh man. Goodness gracious, I'm gonna mess it up. we had compact sets are closed and bounded, and then we know that the converse isn't the case. So I guess if we were gonna take the bait here and believe it's actually easy to show, I'm not sure I do. We should do what? We should take a sequence in the unit ball, right? And somehow produce a convergent subsequence, right?
That's it. That's it.
And convergent as measured by this norm here, right?
Oh, sorry. Yes, no, I remember this now.
Yeah.
Is this kind of like a generalization of the boson wire stress theorem? Every bounded, since we have this norm, every bounded,
Every bounded monotonic sequence is convergent.
yes. Or no, every bounded sequence has a convergent subsequence.
Oh, that's right. Every convergent sequence has a every bounded sequence has a convergent subsequence. I think you're right. So the Bolzano-Weierstrass theorem is actually the thing that we probably want to use. Otherwise, we're going to spin our wheels forever on this.
Okay. This one.
Okay, let's see if we can put that into practice. So let xn, right, be sequence with the norm of xn equal to 1, right, for all n. That would be a sequence in the unit ball, right? And okay, so let's see here. Is that a bounded sequence?
Oh, yeah.
So a little sneaky. Let a sub n equal to the norm of xn be sequence in R, right? Now that
yeah.
that is a bounded sequence of real numbers, right?
Right. Yeah.
So by Bolzano-Weierstrass, there exists a sub nk, right? For which converges to whatever, And that implies that the corresponding subsequence of elements, right, converges to the
We would never have it. It's just
well, yeah, I mean this converges to convert. Well, it's
converges.
sorry. Yeah. One sec. Let me think for a second here. Okay, so what that means is that the absolute value of a sub nk minus a sub 0 goes to 0 as k goes to infinity, right? That's what we mean by convergent subsequence, right? So yeah.
Then you just use the corollary to the triangular property, right? Because that's greater than or equal to the absolute value of a sub n sub k. A sub n sub k is the norm x sub n, and so when we use the corollary, we get the sequence.
A sub n sub k is equal to the, yeah, x sub n sub k. Okay. And then what? Well, I mean, I guess that's just it, right? This, I think that's it, right? So the norm of x sub n sub k is equal to a sub n sub k, right? Which goes to a sub 0 as k goes to infinity. Which I think shows that.
Yeah, but when you so x sub n has a convergent subsequence, right? So it's compact.
But yeah, I think the convergent subsequence is the x sub nk.
Yeah, that's what wait, yeah. We sub the norm, the sequence with the norm of each term is the norm goes to converges. But does that mean x sub n itself has x sub n sub k itself converges? This may just be things through, but
right.
oh wait, just no, we just need a not any, sorry, no, we just need a subsequence that converges in E.
Yeah, I do feel like there's a small gap here.
In the ball, yeah, so it's the ball, yeah, no, that's it, because if it converges, then the norm of it is 1, and so therefore it's in the closed unit ball, and so we found a sequence, or a subsequence, that converges to some value that's in the closed unit ball. In the closed unit ball, and so therefore it's compact, right? Because you just need to find an exists. Sorry, I'm confused earlier. We don't need to say that x sub n sub k is